All right, so today we're going to take a look at section 6.1. The title is the set of rational numbers, and what we're looking at in this section is probably what you are more familiar with calling fractions. So fractions is a more specific term. It's a little bit more narrowly defined than rational numbers, but we'll start there anyway. So fractions are any number that are of the form a over b, as long as b is not 0. That is a fraction. The value on top is what we call the numerator, and the value on the bottom is called the denominator. So fractions can take on any form with any number on top and anything but 0 on bottom. So they can have funny numbers on top, like pi. So if any of you have had trig, or if you remember back to geometry back in high school as well, things like pi over 4, that's a fraction. But it's not a rational number. In order for something to specifically be a rational number, you have to be able to take the number on the top and the number on the bottom and write them as whole numbers. Okay, they might be positive or negative, so we'll call them integers. But you can't have fractions, you can't have radicals, you can't have pi's or e's or anything like that in them and then be considered a rational number. So we're looking at things that are integers on the top and the bottom. This actually includes all of our decimal, let me say all of, but the things that you think of as decimals as well, because they also have the ability to be written that way. For example, we'll do an easy one, 1.5. So 1.5 has a way in which we can rewrite it in fractions where the numerator and the denominator are integers. Therefore, the number 1.5 is also a rational number because it has the ability to do that. Okay? So we're looking at these types of numbers in this section. There's several uses of rational numbers. So we're going to look at 4 of them specifically. The first one is as a solution. So this is a solution to something that would be otherwise unable to be solved with numbers that don't have this form. So a solution would be solving equations like two x equals 1. So if you only had whole numbers, then you'd have to have like 0 and 1 and 2. And if you put in 0, 2 times 0 is not 1. And if you put in 1, 2 times 1 is not 1. And if you put in 2, 2 times 2 is not 1. And there would be no solution. Okay? So it allows us to solve equations that don't have a whole number or integer type of a form available for their value x. More specifically, like application-based are the last 3. So a partition is another way that you see rational numbers used. I'm just going to give you an example. There's nothing special about this example, but we see examples of partitions used all the time. We say something like this: 1/4 of my paycheck goes to gas. Maybe it's more like 1/2 these days. I don't know if you've been to the gas pump lately, but it is expensive. Yeah, so we say a certain percentage, right? We don't think of it as like this, right? This is a partition, but that is a more accurate description of it. We think of it as being a portion of something. We've divided something into pieces, and we're having a portion of it. We think of partitions as well when you think of like, when you eat 1 or 2 slices of pizza, right? It's a portion or a partition of the whole pizza, something. So partitions are very common. Ratio is another one, especially in the field of education. So a ratio that you are familiar with people talking about is the teacher-student ratio, right? So there's lots of ways that you can write a ratio. So to teacher-student ratio is 1 to 10, we'll say this time. So you can write it in words like that, 1 to 10. You'll sometimes see them written as a colon in between, 1 to 10. Or you can see it written as a fractional form, 1 over 10. And those are all different forms. We'll talk more about ratios, but ratios are one use of rational numbers. Probability is something that we'll get to at the very end of our semester, not until we get to chapter 9. But probability is another use of rational numbers that we have. So something like this. When you roll a die, we're just looking at a standard 6-sided die, you have a 1/6 probability, I'll abbreviate, of rolling a 4. Put a number in there you wish, but all right, 1 out of 6 probability. There's 6 sides. One of them is the number 4. So you have a 1 out of 6 probability. There are some really good pictures, too, for thinking about fractions, rational numbers, but we think of them as fractions for the majority of this section. This is on your paper as well, and it shows shaded regions of a diagram. And it wants you to decide what is the amount of the picture that is shaded in. And in each case, they're slightly different on how you should or could think about them. So looking at part A, what fractional portion of this diagram is shaded in?
1/6.
It's 1/6. So if you looked at it quickly, if you were a child looking at it, what might you say that's incorrect? 1/4. Why would you potentially say 1/4? There's 4 pieces. What's the problem? They're not equal, right? They're not equal pieces. So in order to make sense of this, we need to change the diagram. Like visibly, this is helpful, especially for a child, is to change this diagram to show the pieces being equal. And we can do this very easily on this one by simply adding in the pieces on the bottom, right? Those vertical bars on the bottom that then make all the pieces the same size. Okay? And then we say, oh, look, all the pieces now are the same size, so it really is 1 out of 6 equal pieces that we have. How about the second diagram?
1/4.
1/4. But again, if you were just looking at this quickly, or if you were a young child still learning how to do or think about this, what error might you think that it should be instead? 1/5, because there are 5 pieces, but again, they're not the same size. But this one's trickier than the last one because, I mean, they are divided up, right? I mean, like they're closer in size. So while it makes sense to divide this up, again, it actually might be more helpful if I first were to remove these bars, right? And then I were to add in the bar here. Then I can see equal sizes. Now, that's not the only way to do that. I could have divided it up differently. What I could do instead is I could sort of divide it like this and divide all the pieces up. So they're all a bunch of little bitty pieces. That's another option, right? So that would be an acceptable way to think about it too. If I counted these, this would look conspicuously like 3/12. 3/12 is 1/4, which you would talk at some point with a child about how that's the same thing. But it's not an incorrect answer. It's just a different version of it. How about C? Somebody said it, 2/7. Any idea what common misconception a student might think looking at this? Two-eighths is actually really common. Any idea why 2/8 might be common? Yeah? Because there's 8 slices on a pizza. That's exactly right. We think of dividing things in halves much more easily than like dividing something into 7s, you would never divide a pizza like this. Like this would be nuts, right? So our prior knowledge, our experiences in the real world, they do taint what we see sometimes and make us see things that aren't really quite happening and quite there. So it's good to be aware of those kinds of things showing up and to think about why that might happen. Because if you see that the child said 2/8, but you've thought about the pizza, you might respond differently than if you see the child counting and you see them count it incorrectly, right? That's a different issue. So being able to address the issue that they're having is much more helpful. A, B, and C are all the same type of a diagram. They're a whole diagram where part of it's shaded in. Okay, it's a part to a whole diagram. D is actually quite different. There is no whole, right? There's just a collection of objects. And so these are part-to-part descriptions. We'll talk more about these later. But this picture is quite different than those other 3 pictures. So if you're seeing a child being able to do those other 3 pictures, but they get stuck here, that's another clue as to the fact that it's the type of diagram that's causing the disconnect. So on this one, what is the shaded in region? 7 out of 12, right. So we count the blues, there's 7, count the total number of coins or circles or whatever, and there's 12. Any questions on this? Okay, we're going to stop there because it's a very good stopping spot for today.